Welcome to session B of the Introduction to OpenFOAM. My name is Stefan Radl, I'm from Graz University of Technology, and we now will discuss how to use OpenFOAM. So first, let me give you a preamble. How will we use OpenFOAM? Well, as you've seen in session A, OpenFOAM is a package of source code and tutorials. And hence it's natural to set up everything based on a predefined set of tutorials. So if we want to set up a new case, naturally we will simply type tut, use this alias tut to navigate to the tutorials, and then search for a tutorial maybe you're interested in Lagrangian, for example. And we will then navigate to this subdirectory and then look which solvers we do have available and for which solvers we have which tutorials. Here you see with this tree command you see nicely the test cases that we have. For example, for this DPM foam we have Goldschmidt, we're gonna use this later, and for this MP-PIC we have this cyclone test case. So it is we quite have a large number of tutorials. Certainly you will then start combining tutorials to set up a case that is relevant for you. And what is of course important, when you base your work on tutorials, please, it is strongly recommended to first run the tutorial, the original one, and to check if the output is fine. So if the output of the original tutorial is not fine, or the solver doesn't run, it doesn't make sense to continue with this way. So you need to then check what is the problem. Another suggestion is, since OpenFOAM is not GUI based, it is smart to set up scripts. So simple text files similar to the all-run files that we'll see, or the all-clean scripts that realize your workflow. So for example, you would like to pre-process something. You would like, for example, copy some geometry from a directory into your case directory, then mesh, prepare a computational mesh, then run a solver, then do some post-processing, and then finally do some plotting. So scripts help a lot to automate this, and don't use always the input via the keyboard, because you might do a lot of keyboarding there. If you use this kind of scripts, it's also important that you don't duplicate them, so it is smart to have standard scripts, for example, for plotting or preparation of a case, something like this, and that you simply reuse those scripts. This is very important. What is very useful to place them on a cloud server or Dropbox, such that they are synchronized on all of your workstations if you use more than one. And finally, last but not least, tidy up cases. We will see this later. Tidy up cases is important. If you have run something and you just need average information, there's no need to keep all the transient information, for example, or once you've checked that the solver has converged, there is no need to keep this information unless you would like to report it. So always try to tidy up cases after you have run them to minimize the sources of error. What is a typical example how you use OpenFOAM? For example, you have identified a useful tutorial case, and then you would like to sample data from it. Option A is simply Google it. OpenFOAM is used widely, and you will find a lot of hints how to use it. And when you Google for this, you will find a link to this interesting tutorial, and it will explain you how to work with sample. Just a side hint: OpenFOAM was the application was previously called sample. In the latest versions, it's called post-process. So things change, but still you will find useful links that explain you how to use OpenFOAM. Option B is if you're interested, for example, in this sampling stuff, then you simply go to the tutorials directory by using this alias tut, and then you simply use grep to find, for example, sample dict. So OpenFOAM dictionaries are typically called according to the name of the application, and then attached to it dict with D capital letter. So if you use this grab functionality, you can very quickly and rapidly find out where you get, for example, a template for sample dicts if it is not already provided in your tutorial case that you have started with. So this is an important information for you to quickly start using OpenFOAM and all the information that is available for you in OpenFOAM. So yeah, this is quite important. Again, things change over time, but still you will see that you will find information related to sampling in OpenFOAM. What we're gonna do next, we're gonna briefly look over a typical case that will be the IcoFoam case with the name cavity. And what I've done, I went through the PDFs of Hakan Niesel and selected the most essential ones for you, that you can quickly get an overview of how this tutorial will work. And we're going to look at the initial and boundary conditions, the zero directory, we'll see that in a second. Then the constant directory, which contains the physical parameters, the mesh information and the closures. So this is an important directory: physical parameters, mesh and closures. So with closures I refer to, for example, the closures needed to close the turbulence stresses in a Reynolds average Navier-Stokes model, or the subgrid scale stresses in a LES type of simulation. So closures are very generally the information you need to close the transport equations. Then we have the fundamental runtime settings. They are all placed in this control dict. So control dict is a very important file for you. You should understand what's going in there in great detail. And then we have the VF solution and the VF schemes file. They specify the numerical schemes that are used to discretize the governing equations. And the VF solution, they provide the settings for the solvers, for example the linear solvers used to then solve the discretized set of equations. We will also then have the chance to look at some more solvers, and since we are very interested in particle applications, we will look at some Euler-Lagrange solvers, so solvers that use classical computational fluid dynamics to solve the fluid transport equations, but they use a discrete model to approximate the particles, and one of these solvers is DPM-foam, which is very interesting, and the so-called MP-PIC foam, which has been introduced a few years ago and is also very capable solver for solving Euler-Lagrange models. So let us now briefly look at this very primitive standard case, example case. It is the cavity tutorial, and I have borrowed the slides of Professor Nielsen from his training course to explain to you this case. Essentially what we have is we have a wall here, we have a box, and we have on three sides of this box we have walls. Note this is a 2D or ellipsoidal 2D case, and what we do is we imagine that on top of this we drag a plate in this direction, and this dragging plate will induce a motion in the fluid that will approximately go like this. And we are interested in how this flow fight looks like, and you will see it's a non-trivial solution, and yeah, it's the classical cavity tutorial. We use the IcoFoam solver, and we use OpenFOAM 5.x. I've shown you previously how we have obtained this software and compiled it, and the tutorial is located here, and we simply have to copy it. So this is the first part of this session P. So we will, in what follows, then copy this tutorial to our run directory and then start looking at it.